The distribution of shoe sizes amongst American men. The distribution of NFL players at the age of retirement. The amount of protein found in cow's milk. The height of emperor penguins recorded in 2016. The distribution of carrots versus cucumbers found in a random batch in Spain. The probability of the natural variability of monthly temperature at an Australian town in 2019. The number of days against the percentage change in oil pricing last year. The number of weights used at the gym. The distribution of diastolic blood pressure. The distribution of pizza delivery times in New York City last summer. The number of movies that are released every day. The latency measurements of a CSGO competition. The diameter of American basketballs. And the heights of 3,000 convicted English criminals in 1946. What do all of those categories have in common? They all follow something called the normal distribution. And the normal distribution is a subject that tends to strike fear into the hearts of Year 13s for some reason, or anyone who attempts to start it. I think it's because it comes up in so much. Normal distribution is a way of arranging data, or rather, a way that data appears to present itself. Everything I just described, if you plot that data on a graph, looks something like this. And that's not bad for a first attempt, actually. I'll take that. With an x value along the x-axis and some frequency density along the y-axis. And any graph that takes this shape with a couple of specific details define what we mean by a normal distribution. A normal, because it happens so often, distribution of data. Now, this detail isn't going to go very in depth. We will be doing so in the next few videos, calculating inverse normals and how we would actually use this. But for now, let's just have a look at the details of it. First things first, the normal distribution consists of a curve of continuous data. The data is not discrete, otherwise it wouldn't be connected so lovely along a curve. So even though I mentioned earlier things like shoe sizes, even though they're discrete, they tend to look like normal distributions. But a real normal distribution is continuous data only. The next thing to note is that these little tails on either end are asymptotes. They will go on forever without ever hitting the x-axis. And that is a very key part of the normal distribution. There is never a value of frequency density that is 0 ever. The other bit is rather a nice detail that will come up quite often, which is the area under any section of a normal distribution is equal to the probability of that occurring. If this here were a map of heights in a classroom, and I have randomly picked 150 centimeters over here, if I calculated the area here via calculus or some other method, it would tell me the probability that there are, or the probability of being less than 150 centimeters tall in my classroom. What this then means is the area under the entire thing must equal 1. There's a lot being thrown at you at this point. But a couple of other definitions that are very, very important are to do with the mean and the standard deviation. So, the mean of a normally distributed curve, the average result, is always here. It is always the very, very peak of my graph. Standard, my mind went blank. Variance and standard deviations are also very, very key on this graph. If I calculate a standard deviation and I move it to the left or the right of my mean, then something very particular happens in a normal distribution. The area, one standard deviation, plus or minus one standard deviation away from the mean, so here or here, will account for about 68% of all of the data in the system, every time. 68% of the data will be here. If I go 2 standard deviations away from the data, we are already up to 95%. 3 standard deviations, we are up to 99.7%. What this means, if this isn't making much sense to you already, is that the normal distribution is beautifully symmetric. We can always just have a look at our graph, draw some lines when we know our standard deviations, and I'll show you some calculations of that in the next video, and find out how much data are within these different segments. Within 3 standard deviations, we have almost all of the data we could possibly need, and we can guarantee that every time. In fact, when you do scientific research and you write scientific papers, we tend to talk about our results in terms of standard deviations. How many standard deviations away you were from a correct answer or an expected answer tells you how reliable your scientific tests were. And all of this comes from this annoying thing here called the normal distribution.